Okay, as an example of what we have with population and logistics, we have from your example, okay, it says suppose that in 1885 the population of a certain country was 50 million and was growing at a rate or the rate of 750,000 people per year at that time. And suppose also that in 1940 its population was 100 million and was then growing at the rate of 1 million per year. Assume that this population satisfies the logistic equation and determine both the limiting population M and the predicted population for the year 2000. Okay, and 2000 is very much in the rear view mirror, but just looking at this problem, okay, modeling what we have going on from 1885 to 1940, and then looking at how the numbers would project for the year 2000. Okay, so we have, in the case of 1885, okay, how the population is 50 million. And I'm just going to write 50 for the number of millions and for the rate of change in the population. You have 750,000 people per year. We can just write this as 0.75, as in 3/4 of a million. And for what we have some 55 years later, we have in 1940. Okay, now the population has doubled to 100 million. So we will say that P is at 100. And again, in 1940, okay, the rate of change in the population we have in growth of 1 million per year. So we'll just say that dP over dt is equal to 1. For the rate of change of the population, okay, again we have theoretically, okay, we have dP over dt is equal to K times P times the quantity of M minus P. And to get what we have in 1940 and 1885 sort of synced together. Okay, so we have like in 1940, just starting off at this end. Okay, so we got the rate of change, you have 0.75. Here we have is equal to K times P. Okay, so P we have at 50. Times the quantity of M minus P. And again, so we have what's going to be the quantity of M minus 50. And looking at what we have now. Okay, so you have 0.75 is equal to 50K times the quantity of M minus 50. And for what we have in 1940, again we have for the rate of change of the population growth, okay, we have 1 million. And we have is equal to K times 100 times the quantity of M minus 100. And so we can say we have 1 is equal to 100K times the quantity of M minus 100. Okay, so this is what we have at the moment. And notice, okay, we're going to have the same k to be applied for both equations. So we can say that in the setup, okay, if I take what I have from 1885 and isolate k, so k we have at 0.75 all over 50 times the quantity of m minus 50. And if I carry this over and substitute for k for the year 1940 numbers, saying 1 is equal to 100. And again, we have times, okay, what we have in k so far. And again, I have times the quantity of m minus 100. And just taking what we have now. Okay, so I can just get out of the fraction and just multiply the left-hand side of the equation by both 50 and m minus 50. And working across, okay, so if you notice I have 100 times 0.75, so that is going to be 75 times the quantity of m minus 100. And you're going to have like terms on opposite sides of the equation. And the value of m that will make both sides equal, okay, that's going to come out to m is equal to 200. And looking at what we have with m now known to be at 200, now I can express what I have for k this time around. Okay, so again, with the value of m at 200 and the number of millions, say 0.75 all over 50 times the difference of 200 and 50, so it'd be 150 times 50 and 0.75 over that. That's going to come out to a small number where we have k is going to be at 0.0001. And taking what we have now, okay, we got the value of k determined. So again, I have dp over dt is equal to k times p times the quantity of m minus p. And again, m was at 200 and k we have at 1/10,000th. And if we look at separating the variables, so I'm going to take the p times the quantity 200 minus p, divide that, and simultaneously multiply by dt. So I have dp all over p times the quantity of 200 minus p and I have is equal to 0.0001 dt, and integrating over both sides. Okay, and again, you're going to have, going back to the formulas, okay, and this is like a case of dx over x times m minus x, and the antiderivative, okay, you're going to have like 1 over p, which in this case is 1 over 200, and that is going to be the natural logarithm of p, that is the absolute value of p, all over 200 minus p. And that is equal to, again, we have on the other side, so we have 0.0001 t plus c. And if I multiply by 200, the natural logarithm of p, or the absolute value of p, all over 200 minus p, and it's going to be equal to 0.02t, and let's say we have plus alpha, again with alpha equal to 200 times a constant, and 200 times a constant is still a constant. And for what we have treating both sides as powers to which we're going to have the natural logarithmic base to be raised. Okay, so you have e to the 0.02t plus alpha. So you have e to the 0.02t times e to the alpha. Again, constant to a constant is a constant, and we'll just call this beta. So beta times e to the 0.02t. Alright, and I'm just going to go ahead and remove the absolute value notation where I have p all over 200 minus p. is equal to beta times e to the 0.02t. Okay, now, again, we have a couple of population numbers, and now we're looking at the year 2000. And now, I guess technically you could use either P0 for 1885, but we'll go with the closer year since we'll not be looking at such big numbers. And so just kind of keep the time frame a bit closer together. Okay, so we'll just let 1940 be in reference to t is equal to 0. All right, so for the 1940 population, again, that was at 100 million. And we take this into the established equation. So we got 100 all over 200 minus 100. Guess what? E to the 0 is 1. And guess what? We have 100 over 200 minus 100. That is going to be a 100 to 100 ratio. So we had that beta is equal to 1. And for what we have in the result, so we're going to have that P all over 200 minus P. And with beta at 1, so you have e to the 0.02t. And if I look at now with the numbers, okay, if I'm looking at with the year 2000, so in 2000, okay, so you're looking at 60 years from 1940. Okay, and so kind of going back to what we have here. Okay, so we have P all over 200 minus P. We have e to the 0.02 times 60. And it's going to be e to the 1.2. And we'll say that to about the nearest two decimal places. Okay, this will be right at 3.32. And multiplying both sides by 200 minus p. And just for what we have in the follow through. So you have 664 minus 3.32p. And if we combine like terms together, so you have 4.32p is equal to 664. And if I divide by 4.32, we have the population. This is going to be right at 153.7 million.